Swayam Prabha. Digital India. Educated India.
Freshen you up and put you in the right mood to start this new lecture. So we have seen in the previous days that precast construction, precast elements are, the natural field of application of the pre-stressing technologies. Okay. And we know also that concrete is a material which has a good compressive strength and a poor tensile strength. And also, even in compression, concrete is, as we say, quasi-brittle, not perfectly brittle. Perfectly brittle is, in some cases, for example, glass. Concrete is quasi-brittle, but anyway, we have to temper this brittleness. And both for conferring to a concrete element some tensile load-bearing capacity. I say load-bearing capacity, not strength, because concrete has a tensile strength. The tensile strength is very limited. But what we want to do is not to give tensile strength to concrete, is to give to a concrete element some capacity to bear tensile stresses. And for this, and also to temper the brittleness, we use steel. We use, well, let's say we use reinforcement. And the first form of reinforcement was steel, because historically, when the reinforced concrete technology started to develop, there was also a big advance in the steel technology. Steel and cast iron started to be used as structural materials. And the main property of steel was that it was ductile, so could temper the brittleness of concrete. The combination of concrete and steel can work because of a fundamental fact. What is that? Yes, they are two materials that have the same coefficient of thermal expansion, more or less. So that for natural temperature excursion, which is something that even a completely unloaded structural element would experience, they have a similar deformation. So this implies that temperature deformation equally act on two materials and do not induce what we call eigenstresses. So are inner stresses which are self-equilibrated, but locally they can disrupt the continuity of the material. Well, nowadays we have also other kinds of reinforcement, like the polymer bars and so on, which have the good properties of being durable because they do not corrode, or better, let's not say being durable, they do not corrode, but they might have other properties. The bond is different, their modulus of elasticity is lower than that of steel. They tend to be brittle. Their fire resistance is not as good as the one of steel. So, but in different situations, you might use a different reinforcement. So what steel does in concrete is to, as we said, confer to a concrete structural element some tensile stress-bearing capacity. Steel does not modify in any way the strength of concrete, the tensile strength of concrete at the material level. Steel does not prevent cracking. It's not that if you put more steel, your element will not crack. No, your element will crack. And most of all, the fundamentals of concrete mechanics teach us that in order for steel to work properly, concrete has to crack. But when concrete cracks, there are two issues: that you lose a part of your cross section, so your stiffness decreases. Your element becomes much more deformable. And this, as we saw yesterday, is a problem of serviceability. Your structural element may be no longer fit for use. The second issue is that concrete is a porous material. And through the pores, there are fluid exchanges. Fluid means liquids and gases. And these fluids transport any sort of substance depending on the environment where you are. These substances, sulfates, chlorides, carbon dioxide, they activate some processes in concrete which determine aging, corrosion of reinforcement, leaching, and so on. Compared to pores, a crack is a highway for the transport phenomenon. For example, consider that the permeability in a cracked medium goes with the cube power of the crack width. So if you double your crack width, your permeability will increase of 8 times. So 1 order of magnitude, basically. So steel is there to control the crack width, not to avoid cracking. But there may be situations in which we do want to avoid cracking. We made yesterday the example of a tank, of a reservoir. You don't want cracks because otherwise your water or whatever else is in this tank, in this container, will leak through. So the only way in which we can avoid cracking is to pre-stress concrete. What does it mean? Basically, we do want to apply previously, prior that any other action is applied to our structural element, we do apply a compressive stress so that any tensile stress which may come thereafter has first to go to compensate this one and then activate the tensile mechanism. Well, there are some examples in practical life of pre-stressing or even of the alternate of pre-stressing. Barrels are made with wood lintels. That is an example of pre-stressing. You force these lintels inside the steel circles so that they result compressed by hoop stresses, and this gives you the water tightness or the liquid tightness. Here is an opposite example. Think of a bike. The wheel of the bike has, I don't know how do you call it in English. Okay. Well, when you sit on your bike, depending on your weight, you can imagine that the one which is exactly vertical is taking the highest load. But that is a very thin wire, and we'll have a problem of buckling. So how do we avoid this? Those elements are pre-tensioned, so they are under tensile stress, so that when they go on the lower part of the wheel and they take the load, they are zeroed and do not buckle. So there are examples of, situations in which we pre-stress. Well, it's stress. I do not mean that we have to apply a compressive stress. As I showed in the example, you can apply a tensile or a compressive stress. You just pre-stress. Okay. So there are 2 technologies for pre-stressing concrete. We will see only one here, which is the pre-tensioning. The other one is post-tensioning. Today we see the pre-tensioning. And how does it work? Well, this is a very simple scheme. You will see Saturday when you will go to the factory, there are these pre-casting yards that are like, runways, okay? And on those runways, depending on the shape of the cross-section of the element that you have to cast and you have to design it, you will lay down some pre-stressing tendons, which are like cables, steel cables generally. They are loose ones, okay? At the two edges of the pre-stressing runway, you have like two small walls with thick steel platens, which serve to anchor the pre-stressing tendons. On one end, they are fixed. Okay, you have holes there and you fix with some devices the pre-stressing tendon. On the other hand, you have your jacks that apply the, in this case, the pre-tensioning force to the tendon. Well, when this happens in a factory, you have very, severe safety measures which are into place. Because you can imagine, you can have 30, 40 meters long, even more. Because sometimes you cut several elements in series with the same tendon, and then you go to cut for the length of the elements. So there are these several tens of meters long cables with quite some tons of forces inside them. They are free. They are absolutely free. So if they break, they are like a whip which goes throughout the factory. So there is generally a protected space where the operator is there to activate the pre-tensioning. And when this happens, before the concrete comes, nobody should be around. So the situation 0 is here. You are applying a force, as you see here. You are applying this force to the tendon. Okay. Then you cast your concrete. Fresh concrete. Okay, you cover it. Start with the heat curing, which is generally done for pre-stressing elements, because you want a fast development of your strength, because generally in 12, 15, 16 hours, you have to release your pre-stressing. At this moment, the force is only applied in the tendon. The concrete is a fresh mass of material which is not taking anything. Okay. When the concrete has developed sufficient strength, you release your jack. What does it happen? It happens that this tendon here, tends to shorten. If you release the force, it will tend to shorten. This is if the tendon is free, but the tendon is no longer free. There is hardened concrete around it. There is bond. So the concrete opposes the shortening of the concrete. And how does it oppose it? Because between the concrete and the tendon, bond stresses are activated. So the force that you had applied to the tendon is transferred to the concrete cross-section. So at this stage, you are applying a compressive, the equivalent way of thinking to it is that you are applying this compressive force to the concrete element. But generally, we have said one of the purposes of pre-stressing is to avoid cracking. To avoid cracking because we want the fully reacting cross-section because of stiffness reason, because of durability reasons, and so on. So this means that we have to counteract the tensile stresses in the element. And where we do expect the tensile stresses in a typical flexural element, most likely on the bottom part of the element. So we do put our pre-stressing tendons in the bottom part. But when we release the pre-stressing, the element is initially completely, laying out on the runway, on the pre-stressing run. You apply a compressive force, but you do apply it not in the centroid of the cross-section. You are applying it towards the bottom part. What does a compressive force in the bottom part of an element do? It tends to bend up the element. So as soon as you release the pre-stressing, your element does this. It tends to detach from the continuous contact on the bottom and tends to support himself on the edges. But as soon as you do this, the element immediately starts being subjected to its self-weight because you have detached it. So there is never in design a condition where you have only pre-stressing. Because if you have only pre-stressing, okay, well, that's fine. But as soon as you release it, the element acquires what we can call like a pre-camber, and at that point immediately has the self-weight. So this is the, how to say, first stage, first moment for which we have to check our element. Then you have all the transient stages that we have seen, because at that point you lift up your element, you move to a stocking yard, it stays there, then you lift it up back, you put on a truck, you transport to the site, lift it, install on the column or in the structural context where you have to put it, and you start building up on it. If it's a beam in a commercial hall, in a shopping mall, then you will put on the roof, the finishing, and so on. So you will have the application of the other dead and live loads. So the pre-stressing elements goes through all these stages, and we have to check all of that. But you see, along these stages, the way in which the element is working changes. Because look at the figure. This is the typical cross-section, okay, of a roof element in the form of a double T or pi, as we would call. And when you release the pre-stressing and you apply this force equivalent to the pre-stressing here in the position, due to the pre-stressing, you have a distribution of stresses, which is like this. You expect more compression on the bottom and likely some tension on the top. As long as you start applying the dead loads and the live loads, you sum up to this stress distribution, which changes over time, as we will see. You start summing up stress distributions like this. So in the end, you start from a compressed bottom part and a stretched tensile top one, and gradually you change it. And if your design condition is that you don't want to have any tensile stress here, you will have that. Or you may accept some limited tensile stress depending on the design situation. So this means that your element changes its way of functioning. And along its life, the material also changes, both materials also change. And so we have to account this. But the first problem that we have to deal with is, okay, but how much shall I pre-stress? Which means, how big are the tendons that I have to put there? How many are they? Where shall I put them? And how large is the force that I have to apply into them? That is the first design problem that you have to tackle. And this one here, it's exclusive responsibility of the precast structural designer. You will give this information to the designer, who will then take the element and design the structure. But this one, it's responsibility of the precaster. So in order to explain this, I thought it was more beneficial to work with numbers. And I propose you this very simple example. This is a roof element, pre-stressed, quite common shape. You see, you have two stems, and the slab. And the slab is 2.5 meters wide because that is the width of the precast runways. So you tend to exploit all your space. If you go into the width of slab elements in precast, you have either 2.5 or 1.2, because 1.2 is half of it, considering that you might have some spacing in between. That are the numbers that you typically work with. We have decided to make the slab 5 centimeters thick. And these stems are in the form of a trapezoid, which is 9 centimeters wide at the bottom and 12 centimeters wide at the top. Why do you think we decided to make? Yeah, it's just for demolding. You remember the day before yesterday, we said that there are some passive measures to ease the demolding. This is one of them. Design a shape, you know, as if you have a rectangle, you have just to extract the rectangle from the mold. And until you do not fully take it out, you will always have some friction. Here, you just need to lift it up a little bit and it will be completely detached. So it will be much more effective from the demolding point of view. And here you have the dimensions. Let's take the geometry for a while. And the next step is we have to select the material. You know, when you design, you don't have your material there, but you prescribe your material, and you prescribe by performance. As a structural designer, you say, I want a concrete with this performance, not I want a concrete with this cement, with this aggregate, this water, and so on. It's a responsibility of the concrete contractor, the technologist, and so on, to give you a concrete which has the properties that you ask. So we have decided to go for a concrete which has, as it's written here, a characteristic value of the cylinder compressive strength equal to 50 Newton per square millimeter at 28 days. No, cylinder. Characteristic cylinder compressive strength. Cube means 60, more or less. Yeah. Oh, okay. We use FC cube for cube. Okay. No, this is cylinder. It's written here. See, cylinder compressive strength. In Italy, we have the double. In Europe, generally, we have double notation. We call this concrete a C5060. The first number is for cylinders. The second number is for cubes, because we allow both tests, both geometries of the specimens to be used for tests. So it depends on which one you use. You have the two numbers which are already, you know, allowed in the. But this is the characteristic. You know, as we said yesterday, the reason of the lesson of yesterday, so that we have the common language. What is the characteristic strength of a material? The characteristic strength of a material is a value that has 5% probability to be lowered. So if you have a population of the strength of your concrete in the precast factory, you produce this concrete daily and measure the strength. After 1 year, you gather all your data and you see that 95% of your data are higher than 50, and just 5% of them are lower, at least. Characteristic on cylinders, 60 on cubes. Between the characteristic and the average, generally speaking, there is a scattering of 10 megapascal, a little bit less in precast, but. So it means that average strength on cubes should be 68, 70 megapascal. This is an extremely good concrete, but that's true. In precast applications, we want high strength concrete. But then when we design, we do not use the characteristic value we have seen yesterday. We apply some partial safety factor. And the partial safety factor here, you see, it's in the notation of the codes, it's gamma C. Capital C stands for concrete. For cast in place yard cast concrete, gamma C is 1.5. In precast concrete, we are allowed to use, provided we can demonstrate it, 1.4. Like, is specified by codes. In some cases, if you can prove even 1.35. Okay. Why this? Because we have better quality control in the production. Better quality control means that your dispersion, your log normal dispersion is narrower. So your properties, your material properties have a lower scattering. So we are allowed to use 1.4. And then in the design value, we also apply this further factor, 0.85. Why is that? Because concrete, like all, well, concrete is actually, we call an artificial rock. So if you think of a rock, you say it's a non-living matter. But we said that concrete is porous. And through the pores, there is an exchange of moisture, basically, with the environment. This gives rise to shrinkage, but also gives rise to creep. There are several theories about creep and so on. But what does it happen is that if you apply stress to the concrete and keep this stress constant over time, the concrete continues to deform. So you have an initial part of the deformation, which is the elastic part, and you have the creep, the long-term one, which lasts for years. Well, at a certain point, it stabilizes. But what has been experimentally observed is that if you apply this stress and keep it constant, and this stress is higher than 80–90%, depending on the class of concrete, you will experience what is called a delayed failure. So at a certain point, your concrete will continue to creep, but at a certain point, it will break. So in the long term, it's like if your strength will be lower. Because what does it happen is that you compact the structure, you compact the pores, and then you form the cracks. And at a certain point, these cracks, they isolate like some micro columns inside the concrete. And if these micro columns becomes too slender, they break, they fail. So this 0.85 number is to account for this long-term failure effect. So we call the long-term strength. But see, this is another important, and for this reason, I wanted the numbers. We started from a characteristic value of the compressive strength on cylinders of 50. Okay? And in the design, we only use 30. So if you go back to, now I should try. You know, we said, let us imagine that this is our distribution of strength. And the FCK, let us imagine, is here. But with FCD, we have gone even farther back. So it's like if we have done this. So more, yes. That is another thing. That is another thing. In doing this, well, this number here, basically, where does it come from? It comes from the elaboration of production data. But has been, well, why 1.5, why 1.4, and so on? It depends on dispersion of your data. But the concept is that we go from the 5% fractile to the 0.5% fractile. So we have an extremely low probability of being lower. There is another issue that Paul was mentioning. That is the size effect. We will just, tackle it now. We measure our strength on cylinder specimens. Generally, they are 100 millimeter in diameter by 200 millimeter in height. Sometimes we also have 150 by 300, but this becomes unpractical. First of all, because it's very heavy. The other thing is that if you go for higher strength concrete, you need a press with very high load capacity. That is the potential strength of the material. Then the material in the structure is something else. And most of all, there is a phenomenon. There is a phenomenon which is called a size effect, which shows, it's based on fracture mechanics, which shows that, you know, the larger becomes the size of your structural element, the lower its apparent strength in the structure. Well, let's say that for compression, this 0.85 factor also accounts for that. Okay, so we have the design strength, but the design strength, these we use for ultimate limit states. In serviceability limit states, we accept that the material is linear elastic. And in the codes, we have two limits for serviceability limit states. You know, if you make a test on a concrete cylinder and you plot here the nominal stress, which is the applied load divided by the cross-sectional area. Remember, you never measure a stress. Stress is a quantity that we cannot measure. We measure a deformation. And in load cells, through that deformation, we convert into a load. The stress we always calculate based on an assumption. And the assumption under compressive load is that the stress are uniformly distributed over the cross-section. So the stress is load divided by area. Then when we make the test, we put two steel plugs here, and we put an instrument here which measures the deformation, the shortening, and we plot delta L over the initial length here, which is L0, and we call this the deformation. So what we plot as stress strain deformation is something which has already assumptions into them. But anyway, typically, the concrete behavior is like this. So we do know that up to about 50% of the strength, the behavior is linear elastic. Now I have to cancel. Okay, for serviceability limit states, we have two stress limits in concrete. Let's start from the lowest one. 45% of the compressive strength. This limit is a limit. It's not truly a limit of the material. The material can go higher. But it's how to say, operational one. Because we have said that concrete creeps, okay? And what does it mean? It means that when you have to go to calculate the deformations of concrete, you have an elastic part and the creep part. Up to a certain stress level, the creep part is proportional to the elastic. If you go beyond this stress limit, the creep part starts growing more than proportional to the elastic. So we want to keep the stress low so that we also control the growth of the creep strains. We control the growth of the creep phenomenon. This limit has experimentally been identified in 0.45, in 45% of the compressive strength. So keeping the stress below this limit, helps you in controlling the creep. You cannot avoid creep, but you can control. If you keep the stress low, your creep will grow lower. What if it's higher? Well, if it's higher, you must abandon. It's a matter of, you know, making more complicated calculations, because you can no longer say the creep strain is proportional to the elastic and you just have a 1 plus something, 1 plus phi coefficient. You must make nonlinear creep calculations, which I can guarantee you are not that simple. But besides the complicate of the mathematics behind that, it's a functional issue. You want to keep the creep strains controlled, because otherwise your element continues to deform, to deform, to deform. And there has been, if you go on the web and Google Palau Bridge, it was a bridge which collapsed because of excessive creep. Because if you have a flat arch and the arch starts to creep and creep and creep and creep, at a certain point, it's no longer an arch. It becomes a slab, a three-hinged beam, and it falls down. And the Palau Bridge collapsed exactly because of this. If you go to the website, to the internet and Google it, it's okay. But which are the loads which produce creep? Because as we said, creep is a phenomenon. Creep is a phenomenon that requires some level of stress to stay permanently there. So surely the dead loads, the self-weight of the beam of the element, produces creep, because if the element exists, it has a weight. We live in the gravity field of the planet Earth, so we cannot avoid that. But think of this room, for example. We are here now, this morning, then we go for lunch, then we come back, and then by 5 this afternoon, there will be nobody else here until next morning. So we have occupied this room for how much? 30–40% of the time, every day. And then there are some days and where there is nobody. There are some days where this room is more full, and some days where this room is more empty. There are some holiday periods. Saturdays and Sundays, nobody comes here. So the live load for this room has a fixed part, which are the floors and the furniture, but also a variable part, which goes back and forth. So not all the part of the live load produces creep. Only what we call the quasi-permanent part of the load. And in the codes, you have some factors which tells you, okay, for apartment buildings, the quasi-permanent load is 30% of the full load. If you go into, public offices, or even you can say movie theaters and so on, that is a little higher. And you could say, but in the movie theater could be even probably less working time than a classroom. Yeah, but in a movie theater, you have more crowd. And the consequences of a failure will be more impactant. So in that case, probably the quasi-permanent share is 50%. But if you go to a warehouse or to a library, then it's 100%, because the books in a library stay there forever. Or in a warehouse, or in the storing part of a shopping mall, you have goods stored. So you have in the codes tables which help you in deciding this. So this stress limit, the important thing is that this stress limit has to be checked under the quasi-permanent combination of actions, where you have dead loads and only a share of the live loads. For example, wind. If you have wind, it does not enter into this, because wind is a dynamic variable action. In countries where you have also the snow load, also in northern India, it depends on the altitude. In some cases, if you have a lower altitude, the snow load, the quasi-permanent fraction can be 0. But if you go altitudes above 2,000, 3,000 meters, then likely you might put a fraction of the snow load as a quasi-permanent load, because you can expect to stay there for several months during the year. In some cases, you have even perennial, but okay, on buildings, you have measures to take it out and so on. But you have to check for that. So this is the quasi-permanent situation. But then we can have also what we call a rare one. Rare one is one in which you have the dead loads and so on. But can there be a situation in which, for example, this room is full, and even more full, and it lasts for 2-3 hours. Okay, we have to check also this event. So in which you have the full dead loads and the full live loads. We call it rare combinations. But in this case, we are a little more generous with the material because we say, okay, you are experiencing this only for a part, a very limited part of your service life. So we allow, as you see with concrete, a little higher percentage of the compressive strength, 60%. So this is very important. You check your element not only for stages of his life, but also for different situations which may happen and correspond to different scenarios. Think, for example, of a bridge. Okay. In bridges, I will say if they are pre-stressed concrete bridges, the 60% of the total load-bearing capacity is for the self-weight, more or less. Okay, so self-weight. And then you have also the superstructure because you have the slabs, the roads, and so on. But then you have the vehicles. And the traffic vehicles is what we call a cyclic. It goes on and it changes and so on. But there is an average value of that traffic load, which we can assume stays there forever. So that is what we use in the design situation. Okay? It's the rare one, yeah. Rare one, yeah. Without load factors are 1. Okay? Whereas in the quasi-permanent, you have load factor 1 for the dead loads, and this 0.3, 0.5, 1, it depends. It's not a load factor, it's a combination factor, which gives you the percentage of that load, which you can consider as quasi-permanent, as if it was permanent. Okay, yeah. Yeah, this is the Eurocode terminology and also the FIB model code terminology, so it's international. Okay, so that is compressive part. Then we know that concrete does not have a reliable tensile strength. It's not true that it does not have a tensile strength. It's simply not reliable. But if you have to make a crack check, if you have to check whether concrete cracks or not, we have just to assess whether the tensile stress is higher or not than the strength. So we need to calculate the tensile strength. Well, we also need to measure, but measuring the tensile strength can be complicated. Most easy way, you make some splitting tensile test. So, but as I said, when you design, you don't make tests before because the material will come after. So you have to set down a certain values for that. And in the codes, you find some formulas or analytical relationships which correlate the tensile strength and the modulus of elasticity for concrete. They correlate it to the compressive strength. That has been the philosophy. You say, okay, since when I ask for the performance of concrete, I ask for the compressive strength. You want a concrete, well, I know that here, what is M1, M30, M40, something like, yeah. It's similar. So that number is the compressive strength. That is only what you ask. But from that, you must be able to calculate, to derive in the design stage, the other properties that you might need. And these relationships, these analytical relationships are based on database, on best fitting procedures, reliability analysis, and so on. Nowadays, you will use AI, you will use a neural network, and so on. By the way, they have a good reliability. They are confirmed for broad range of cases. And you see the tensile strength of concrete, does not depend linearly on the compression strength. It has been found, or it has been set. Well, this is the Eurocode. I think that the ACI code uses the square root here. But here you see in the Eurocode, we have the cubic root of the square. So it's like power 0.67. And there is a coefficient here, 0.3. this is a best fitting. There is no physics behind this. Well, the only physics is that they do not linearly depend on each other. So this is something I was telling yesterday also for Young modulus that we'll see. It's not that if you double the strength of your concrete, your tensile strength or your Young modulus will double as well. They will increase, but not proportionally. And you see that 50 megapascal characteristic compressive strength concrete has an average tensile strength equal to about 4 megapascal. But average means that we are here. Oh, no. Average means that we are here. Then from the average, we must go to the characteristic and then to the design. So for the characteristic, the code says multiply by 0.7. Yes. Correct. Yeah. Through this formula, you use the characteristic compressive strength, but you are getting the average. And in order to get to the characteristic, multiply by 0.7 as well. But then this is the direct tensile strength. Okay, direct tensile strength. If you want to experimentally measure, you should make a prism of concrete, glue or grab it, and apply tensile force. Very, very difficult test, very unstable. You need very precise control. You need very stiff machine and so on. But also in our structural elements, are we really experiencing direct tensile forces? Well, we could have some ties, concrete ties, but so what we generally, where we do experience tensile stress is because we have a bending action. And in a bending action, the distribution of stresses over the cross section is like this. You have compression stresses here, sigma c, and you have tensile stresses here, which we call sigma ct. It's true that when the concrete stress arrives at that limit, you start forming a crack. But the bent cross section has this advantage that you arrive at the maximum stress here, but you see you have another significant portion of the cross section which still can help. So you can have some cross-sectional stress redistribution. And what does it happens is that in reality, when a beam really fails, think of an unreinforced beam, okay? When it really fails, it's not when you get here, but it's when you get to a distribution of stresses, which is something like this. Because concrete softens after the peak, after the cracking, there is some life after. So, I don't know. Well, you ever play to pull the rope? So on, you have two teams, and you pull the rope on either side. Okay. So you always have in a team the stronger guy, and you have the weaker one. Weaker one pulls, but at a certain point he shouts and say, "Okay, I am done. I cannot do anymore." But if up to that point, all the people in the team are pulling in the same way, the weaker one has arrived at the maximum capacity, but the other ones not yet. So they can help, and they continue to pull. So that is the same mechanism. There are parts of the cross-section that you have not fully yet engaged that help those who are at their limit to go a little bit forward. And how can this happen, to go a little bit forward? This happens that they can deform a little bit after having cracked, but they give back some stress. So that is this mechanism that we have here. So there is some redistribution of stresses. But we want to keep the things simple. It's much easier to work with a diagram like this than with a diagram like that. So what we do is that in flexural elements, we fictitiously increase the tensile strength. And we call it flexural strength. Well, in this case, if you go to the codes, the factor which allows you to go from the tensile strength to the flexural strength depends on the size. And the higher, the deeper is your beam, the lower is this factor. So there is another way in which the size effect is taken into account. But for the sake of simplicity, you are allowed to say, at least in a design stage where you can make some preliminary calculation, then you refine that. You say, okay, the flexural strength is 30% higher than the direct tensile strength. And then, okay, if you want to go for the design, you have to apply the safety factor also there. It's 1.4. So you see, this is something that you have to set. These are your tools. Okay, it's like if you have your own workshop and you have all the hammer, the screw, the whatever you need to make your hobbies and so on. And also we need to calculate the Young modulus of the material. Also, the Young modulus does not depend linearly on the compressive strength. The formula that we have here, once more, it's a best fitting. And it has been shown that this fits the data. You have the average strength there, FCM. You say, well, I don't know how much FCM is because I prescribed the characteristic. So the code tells you, okay, in this stage, take the average as the characteristic plus 8 megapascal on cylinders. Yeah, thank you. So you see, we have, put the numbers, we have 36 gigapascal. Okay, now just try for your own idea, just to see how these properties change if you change the grade of concrete. So imagine that you are working with a very high strength concrete because you have decided with the contractor that you want to use it. You go for 100 megapascal concrete. Okay? And try to calculate for 100 megapascal concrete, how much is your Young modulus? For compressive strength, yes, but not for tensile. Tensile strength has a completely different code chapter. For compressive strength, yes. For compressive strength, yes. Well, even this you can use, but then it's just the first part. Then you have to add something else. Yeah. So has anybody come up with a number? 44.9, 45 gigapascal. Okay, you see, we doubled the compressive strength of concrete. We went from 50 to 100. And what happened to the Young modulus? It went from 36 to 45. That is just 25% increase. So really, that is you can also understand that, when you use high strength concrete, your design problem may not be any longer a strength design problem, but becomes a stiffness design problem. And this is because of two issues. Well, if you have used a higher strength, the main reason is that you want to reduce your cross-section dimensions. So your element becomes more slender, which means more deformable. But at the same time, you know, you cannot say, I have used a twice as much strong concrete, I divide by 2 my area or my modulus of inertia, flexural modulus, and so on. Well, it depends, because your stiffness has not increased twice, has increased only by 25%. But this is for concrete at 28 days. But we have said the first stage for which we have to check our, concrete pre-stressed structural element. So we have also to specify, when we are in pre-cast pre-stressing, we do not only specify the concrete at 28 days. We have to specify also what properties do we want at 16 hours, because that is the first moment in which the element will start being checked. And we do require, that is it's the structural designer which states this. We require that this concrete at 16 hours has a 30 Newton per square millimeter characteristic compressive strength on cylinders, which means about 35, 37 megapascal on cubes, characteristic. Then the procedure is exactly the same. Well, which differences do you see between this slide and the previous one? You have both of them. There are some differences. .7 instead of 0.6. Why this? What? Yeah, that is. So this moment, these 16 hours, okay, they last for, and it's just a very limited moment in which you release the pre-stressing and move it. Over time, it will increase. So you can accept some higher stresses in this stage. Also, because there is another important thing. Yeah, the same day. Yeah, because you cast the afternoon, and in the morning you go there, because in the same afternoon you cast the new element. But you see, let's go back to this situation. When you release the pre-stressing, you expect stresses like this. So the compressive stresses are in the bottom. Whereas in the other design stages, you expect that because you apply the load, the compressive stresses will go on the top. So at 16 hours, 20 hours, or whatever, you accept the higher stress, but in a region where that stress will be progressively be relieved by other load situations. So that is the reason for which we do also. But there is also another difference. Well, modulus of elasticity changes because the strength changes, but the formula is the same. Huh? Alpha C is 1. And why? Well, there are no long terms. This is a transient design situation. It will last a few days. And after that, it will change. And for this reason, we do not make a check under the quasi-permanent combination of actions, because it will not mean anything here. In this stage, there is only the element. There are no other loads. So the rare combination or characteristic combination and the quasi-permanent combination, they do coincide. But this situation is really very short to account for creep. So we do not take into account anything about creep. Yes. You measure it. The precaster is obliged to make 2 tests each day. He can make on cubes or on cylinders, but he has to measure that. Any precast factory has its own lab. It can be more or less equipped, but at least you must be able to make a compressive strength test, and you measure it. Because there is, well, there are some formula we have seen. The maturity based is for your own check to decide whether it's good enough. For example, if it's not exactly 16, but it's 14, or if you need to go a little bit more. But maturity check is for internal control, but has no legal validity. To have that, you must have the tests, and you must keep the logbooks for these tests. So this is for concrete. Let us now go for steel. Well, the steel that we use for pre-stressing is completely different than mild steel that we use for regular bars. It has a different production process, which, you know, makes it stronger, but also in a sense a little bit more brittle. And it comes not in form, well, you can also apply pretensioning to bars, but the most common way in which you use, because they are easy to be handled during the construction stages, are these 7-wire tendons. These are the most common ones. 7 wires, you see the cross section there. You have a central straight wire, and the other 6 are twisted around them. So it comes like in a rope. Okay. And well, that is one of the situations in which throughout the world you keep the imperial system of units, because the diameter of pre-stressing tendons is given in inches. Okay. The most common ones are the 0.6 inches tendons. 0.6 inches is about 15 millimeters. Okay. As I was saying, the properties of steel for pre-stressing we call harmonic steel in Italy. Harmonic because it's similar, you know, you use the same wires in piano strings or in musical instrument strings. It has to be very high quality, very pure. You see that the rupture strength is around 1800, 1900 Newton per square millimeter, because it's produced with some thermal treatments. Regular steel for reinforced concrete has a rupture strength, not yielding, rupture 600, 700 maximum like that. And steel for carpentry steel, the rupture is 500, something like that. Maximum, generally, we have 400 or 300. This is much higher. But what is the effect of the thermal treatment? You see, this is a typical curve of a tendon. The effect is that the yielding disappears. There is no clear yielding. So conventionally, we identify another strength limit that we call equivalent yielding strength. Okay? And this is the strength to which, if you will download your tendon, residual deformation, because the material, if elastic, if you load and download, you go to 0. But if the material is non-elastic like this, when you load and unload, there is some residual deformation remaining there. So the equivalent yielding strength is defined as that stress to which a residual deformation upon unloading of 0.1% does correspond. And this is 1580 Newton per square millimeter. These are data that the manufacturer of the tendon gives you. And well, it gives you not on a sheet of paper written, it gives you certificates of an official lab. In our lab, in our university, we make tests to certify these tendons. And we make tests in the lab, but for steel, we also our personnel goes to the factories worldwide, because you have to inspect the production. So every now and then, periodically, you go there and say, okay, let's pick up 2 bars from that lot and let's test them and so on. So you regularly certify that. The nice thing I will tell you, when these tests on the tendons are made, they are generally made in the afternoon, late afternoon, where there is less personnel, because when a tendons break, you really hear like a bang. And sometimes I would not say that there is a micro tremor in the building, but it can be, depending on the diameter of the tendon, because the same equipment that you use for tendons, you use also to test cables for cable cars, which are much, thicker. But this is just to tell you that. Obviously, these are characteristic. We have to go to design. And here we have another partial safety factor, is gamma S. S stands for steel. You see, we use at 1.4 for precast concrete. We use 1.15 for steel. What does this come from? What does this mean? It means that the dispersion of the data for steel is narrower than for concrete. Steel as an industrial process of production. Concrete, even if precast concrete is industrially produced, you still have some kind of craftsmanship into that. So you have a higher dispersion. Steel has a narrower dispersion, and this results into a lower safety factor, lower partial safety factor. Young modulus, we denote it with EP and not with ES. S is for steel, P is for pre-stressing steel. Why? Because as you can see, it's a little bit lower than what we generally use for steel. For steel, we use 200, 205, 210 sometimes. Why we use a lower Young modulus for pre-stressing steel? Because as I said, this is not a bar. It's like a rope. So when you stretch it, first of all, you have an initial straightening of the twisted wires, and then you start stretching all of them uniformly. So this results in a slightly more compliant response. So this is not the Young modulus of the material, I would say. It's the Young modulus, upper and Young modulus of the product of the tendon. So these are all issues. Designing pre-stressed concrete is not simply that you have an additional force on the bottom and that's it. It's really, you have to take into account the different things starting from the material design philosophy. Okay, so now we are done with the material. Okay, now let's go, and I'm going through this. This is also the structure that you will ask for a design report. If you are a certified, for example, as an engineer, you might be asked to make a final check on something which has been built, and you make some load tests there, but you also must have the design report. Design report must have this structure: description of the problem, materials, load analysis. Do not trust the design reports which come in a huge bulk of paper which full of numbers or pictured colors from a computer, from a software. Design report must allow you, who are a completely independent person, you have never seen the structure, you have never seen the material and so on. Well, you can have some during the construction inspection, but generally you are a completely third party. The design report must allow you to go back and make the same reasoning that the designer has made. So as a designer, you must be as much clear as possible, but as a final checker, you must pretend this clarity. Okay. So now we go for load analysis, and first thing that we do, we have to calculate the self-weight of the element. So if you go back to the slide where there is your cross section, you see that here 2.5 times 0.05 is the area of the slab. 2.5 meter wide, 5 centimeter thick. Plus 2 are the two stems. The two stems are trapezioids, 9 centimeter thick at the bottom, 12 centimeter thick at the top, 45 centimeter thick deep, divided by 2 because the area of the trapezium. So it's simply a matter of elementary school geometry, not more than that. This is the area of the cross section, and it comes in square meters. You multiply by the specific gravity of reinforced concrete, 25 kilonewton per cubic meter. So what do you get is a self-weight per meter. So if you design your This number here is what you will call G. Generally, we denote the self-weight as G for gravity. So that is your self-weight load. Well, then we have to consider that when this element will be installed in a structure to make, for example, the roof of a building, likely also for seismic reasons or so on, we might have some topping on it, 4 centimeter reinforced concrete topping, which is this one. And then, well, if it's a roof, you might add up some waterproofing, thermal insulation, and so on, but these generally do not count too much. So you see, in the end, the self-weight of the element is 5.5 kilonewton per meter. But in the final configuration, when the element will be fully installed in the building, the dead loads will be 8.5 because you will add that up other 3. Also, just have a look here. The 5.5 kilonewton per meter. Try to, well, just calculate this number here, 2.5 times 0.05 times 25. Just to see the self-weight of the element, how much does it pertain to the slab and how much to the stems? 3.125. So you see 60% of the self-weight is just that thin slab and 40% are the stems. Just to have an idea. Okay, so these are the dead loads. And then we have the, variable loads, the live loads. In this case, you just have snow load. Well, this was supposed to be in northern Italy. And the snow load there is 120 kilos per square meter. Well, actually, there is a story also behind this number. It changed during the years. And one major change happened after 1985. There was a major snowfall. I remember quite well because I was middle school or initially high school freshman, and we stayed at home for 1 week. I lived in southern Italy where it never snows. It snowed there also very nice. Everybody of my generation remembers this heavy snowfall. But what happened was that several buildings, especially there was in Milan a sport hall, which shape that did not allow the snow to fall down, but kept the snow like in a tank, in a basin. That building collapsed. So after that major snowfall, the snow loads in the codes were increased, just to take into account that you can have some exceptional meteorological events and you have to compensate for this. Luckily, it snowed. There was no, I think it was basketball sport hall. No match played there, no people there. So it just was the sport hall that collapsed, but that was that. Well, there is another thing. And you say, okay, but if I have to inspect my roof, some workers have to go there, or periodically you must, refresh your waterproofing, because waterproofing generally can be done with bituminous material, and they have the problem of aging under sunlight. They become brittle, they start breaking. So every certain number of years, you have to go there and make a new waterproofing. How do you take into account this? Yeah, there are some live loads. If you go in the codes, there are some live loads which are called maintenance loads for roofs. Because one thing is that if you have a garden on your roof and you can hold parties, then you put on the roof the same loads that you use for, if you have a garden roof, for example, you have soil and so on. But if the roof is accessible to people, you have to consider it like a cinema or movie theater or sport hall, so for crowd people. But if your roof cannot be normally used, you have any way to put on them the maintenance loads. And the maintenance loads come in 2 forms. There is a distributed load, but there is also a point load, because if you are there, for example, with an equipment, this equipment can be very heavy and is a concentrated load. But generally, in northern Italy, the snow loads are worse than the maintenance loads. But there may be cases, for example, in southern Italy, where the snow loads are lower at 0.6 kilonewton per square meter, and the maintenance load in some cases can be worse, depending on what kind of. This is also just to show you that before going, we have not done any structural design calculation so far, but if you don't lay out these assumptions, you will make calculations which are not represented. So before going into a software, into a calculation and so on, have very clear what is your problem. As NRG, the first lecture in the morning, say, go to the job site, go and have a look to that. Where are you going to build this building? Because this is, if you set the framework in the wrong way, your calculation can be the most exquisite and perfect buckling theory, lateral, whatever you want to do, but they do start from assumptions which are not fully representative. And now, now some calculations come into play. Because we have the area of our structural element, but we also need to know the moment of inertia, the flexural modulus, the position of the centroid, and so on. Because if we have to make our structural design calculation, we need all this information. So what I did here, well, this is a table. This is a very simple. You don't need any special tool. It's just a worksheet file, okay? Excel or whatever you want to use. Well, this is not a rectangle for which you know that the moment of inertia is bh cubed by 12, bh squared by 6 is the flexural modulus, centroid at the middle. This is a composite cross-section. You simply have to calculate that. And I have decided to divide it into a slab. This slab is a rectangle. The ribs, I have divided them into 2 rectangular parts and 4 triangles, one on each side. While I have decided to go for rectangle and triangles, on the other hand, also the trapezoid is easy. Well, simply because I do not remember the position of the centroid of a trapezoid, but I remember that the position of the centroid of a triangle is at 1/3 of the depth. So that is simple. That is simple. Very, very easy. Well, if you Google centroid of a trapezoid, you find it as well. But sometimes you just want to go. So I took as a reference, we took as a reference here, in order to calculate the position of the centroid. Let's use a different color than red. Let's use the green. I put my reference here. I start from there. And you see, I have the slab. The area of the slab, I use millimeters here, is 2,500 times 50. And its centroid is at 25 millimeter, measured from the top. It's a rectangle, it's a mid-depth. If you multiply the position of the centroid by the area, you get the first order moment, first order area moment. So this column here is simply the first column multiplied by the second column in an Excel way of thinking. Then you have the ribs. The ribs are 2. They are rectangles, 90 millimeter wide, 450 millimeter thick depth. Where their centroid is positioned here at mid of their depth. So you have to go down of 50 plus half of 450, which is 225. 50 plus 225 is 275. And then you have the triangles, these small wedges. This is 4, because you have 1, 2, 3, 4, times 15. 15 is this. 15 is this. Because at the top, the trapezoid is 120, minus 90 is 30, divided by 2 is 15, times the depth, which is 450, divided by 2, because it's triangle. This is the area. Where is the centroid position? At 1/3 of 450, starting from the top. Plus, you have to add the 50 millimeters of the rib. So 1/3 of 450 is 150, plus 50 is 200. Then you sum up all the first order area moments, you sum up all the areas. If you divide this by this, you have the position of your centroid. So the centroid of your element is at 128 millimeters from the top. So it means that it's somewhere like here. So the centroid of this cross section is in the empty space, but it's there. And why do we need the centroid of the position of the centroid of the cross section? Let's see if we, because when we have to calculate the moment of inertia, we must refer to the centroid of the cross section. So once more, to calculate the moment of inertia, oh, there is something missing here. Yeah. Yes. Okay. Yeah. Well, we calculate the moment of inertia. What I do here? Yes. No. It's okay. So the slab. B T cube by 12, plus you have the transporter, which is the area, times the square between the distance of the two centroids. 128 is the distance, is the position of the centroid of the whole cross section. 25 is the centroid of the slab. So now what is missing here is that you have 90 times 450 to the cube by 12. Add this in your slide. So you have here 450 to the cube by 12. Plus you have once more the area times the square of the distance between the two centroids. And here you have 4, the moment of inertia of the triangle is 450 to the cube divided by 36, plus once more the transporter. So that is the reason for which we need to know where the centroid of the cross section is. So you end up with calculating this moment of inertia. And if you divide the moment of inertia by the distance from the centroid of the top, you get the upper flexural modulus. By the distance from the bottom, you get the lower flexural modulus. So this was all the preparatory work that we needed to design the pre-stressing. So we had our geometry, we made the choice of the materials, we made the load analysis, and we calculated the geometrical characteristics of the cross-section in terms of area, centroid, moment of inertia, flexural moduli. These are the tools that we are going to employ now. I think it's coffee break time now. It's 10:30. I'm feeling that I need some coffee. So we will use these quantities to start with the design, okay?